Okay, so we're going to look at chapter 4. And today in chapter 4, we're going to talk about linear regression. We're talking about linear regression. We're just talking about, we're just building up off of what we were talking about with the correlation, and we're going to take it a step further. So we're first going to start with what we call the least squares regression line. This is the line of best fit. It's the line that's best going to describe the linear relationship between x and y. Its name, least squares regression line, comes from that it is the line that will minimize the sum of the squared residuals. I'm going to show you a picture to go along with that here in a few minutes. But it's called the least squares regression line. So it minimizes, it's the least of the sum of the squares. So here's the squares, okay, of the residuals. And like I mentioned, it's their line of best fit. There's different lines we can study. We are just choosing to study the least squares regression line, okay? We can use this line or the equation. I'm going to put that here to predict values. So we can use this equation just like we would in algebra, and we can plug some x value, our explanatory variable, and into the line or into the equation, and we can solve for y, which is the response variable, so we can predict some y values. So let me give you a visual of what we have going on, and I may zoom this in here in just a second so we can see. But this is my explanatory, my x variable down here, and over here I have my response variable, my y over here. Okay, so when I'm looking at this, I'm going to try to change colors. I don't know how helpful it's going to be. I might have some scatter plot like this. Okay, let me put one there just to change it up a little bit. Okay, my line of best fit would go somewhere down the middle of this thing. Okay, it would probably be like that. Okay, somewhere's down the middle. And this line, so I'm going to say this is my least squares regression line. That over here. And, or my line of best fit, we can call it. This line always goes through the point x bar, y bar. Now remember what x bar and y bar stand for. X bar and y bar, those my sample means for my x's and my y's. I'm just zooming this in a little bit so we can see. I might even zoom it in a little bit more so we can see what we're looking at here. Okay, so always goes through the means. And let's take a look at a data value and what we're looking at, because I brought up over here, I'm going to slide my paper, this residuals and what we're talking about for that. Okay, so if I have some data value and say this data value is, I don't know, I'm just gonna choose one, maybe right here, okay? And I'm gonna just do like a dotted line down here. And this would be my x1, right? So this is the x that goes with that point, that individual. And if I just brought my dotted line over to my y-axis, put the dotted line there, this would be y1, right? Okay, so that would be point x1, y1. Now, what happens if I don't actually have a data value there, but I want to know what y would be if x is this amount? Then I would have this, I would take that x value and go up to my line here, okay? And I would read my data value from my line. Now, it's predicted. It's not going to be the same as one of my data points most of the time, right? Once in a while, like this one right here, you can see that data value is on the line, so that would read the same. This value right here is called y hat 1. So the point on the line would be x1, y hat 1. And y hat is the predicted value and y1 is my actual value. So what we're looking at is this difference in here. I'm like pulling out all sorts of colors here today. So what we have here, and I hope we can see it because I'm kind of trying to zoom it in a little bit. What we have right here is the difference, right? And that is my error or my residual. So let me draw an arrow, and it's error or residual right there. And that is equal to my y1 minus my y hat 1. And I know you guys can't see that because I'm zoomed in too far. Right there it is. Right? So the error, the difference between an actual and a predicted, is going to be the residual. And that is what the least squares regression line is minimizing. Okay? So I'm going to zoom this out so we can see the whole paper again. So that right there is what the least squares regression line is going to minimize. The sum of the squared residuals, that difference between an actual point and my line. Now, it's squared because you can see some points are below the line and some points are above the line. So you're going to have some positive and some negative error or residuals. And if you just added them up, if you just summed them up, they would cancel each other out, right? So you would square them, so they're all positive values, and then look at the sum. So that's why it's squared residuals. And that's what this least squares regression line is doing. It's minimizing that, that difference there. Okay? So let's take a look. That's what the visual looks like of it. Let's take a look at the equation. So we're going to go back to algebra a little bit here. So our equation of our line if you recall from algebra, it's y is equal to the slope times some x value plus my y-intercept, right? And in algebra, we looked at y equals mx plus b for that equation. And now in statistics, we're looking at y hat is equal to ax plus b, or we may see it as y hat is equal to b1x plus b naught. Okay. So this little guy, I'm just going to write it over here. Y hat is equal to y hat, just so we know the notation. This is a y with a little hat over him. We just say it, y hat. B, the little 0 is B naught instead of B0. Okay, so we are familiar with that, some of the terms. Now, we're not going to calculate this by hand. We've done this enough in algebra class or pre-calc, right? So we don't need to go through these calculations. I am going to show you. We know how to find the equation of a line with 2 points. Hopefully, we know that stuff. We don't need to do that again. We've done that enough. We're going to use our technology to do this for us. I'm just going to give you some information based on this bottom one, the B1 and B naught. So B1 or A is equal to our R value times the standard deviation of Y divided by the standard deviation of X. This is my slope. That's the calculation for my slope. We don't need to calculate it because our calculators will do it for us. Okay, I'm just giving it to you. So that's B1 or A, and B naught is my y-intercept, or here would be B, is going to equal my sample mean of Y minus B1 times my sample mean of X. And this is my y-intercept. Again, we're not going to use this calculation either. I'm just showing you, and I think we already know how to do most of this from algebra, so we're gonna not do it by hand anymore, okay? So remember SY, maybe I'll write it over here, SY and SX, these are the sample standard deviations, and X bar and Y bar, my sample means. Just as a little key code for us, in case we forgot that from last class when we talked about them. So that's the equation of my line. If you're using your calculator, you're going to see this AX plus B. I just write from calculator. Here, okay? So let's take a look at how to interpret A, my slope, and B, my y-intercept of my statistics equation for y hat. Okay? So I just also want to mention this y hat here. We use that because that's my predicted value, right? And my line gives me predicted values, not actual values, unless, of course, the point from the scatter plot is on the line, which happens occasionally. Okay, so let's talk about interpreting these values. We're going to look at interpreting the slope and the y-intercept. Now, I'm going to give you templates, and I've done this on some of the assignments, the team assignments. I'll give you a template set statement or sentence you can use. You may use that throughout the course when you're doing these, but you don't have to. I just want you to know you don't have to use my template sentences. You can come up with your own statement, and that is great also. So for the slope, I want you to think about what the slope is. It's the same thing as in algebra. So what we're looking at is for each unit increase, it's always about that increase, in my x variable, so in my explanatory or my predicted variable there, the y variable, my response variable, will either increase or decrease by the slope. So underneath, I just write what you're going to plug in to these statements, okay? And I don't want you to say for each unit increase in x, the y is going to increase by 5. Like, I don't want that. I want you to say for each inch increase in height, the weight will increase by 5 pounds or something like that, okay? So I really want it in the context, that's called the context of the problem or the wording of the problem. That's what I'm looking for, okay? Let's talk about the y-intercept. Again, it's the same meaning as in algebra. When x is 0, y is that value, okay? We're just going to put it in terms of the problem. So my y-intercept value, so whatever b is what I'm talking about here, is the response variable. That's my y. When my explanatory or my x variable is 0. It's just writing it out into words. I know in algebra we've done this before. X equals 0, y equals 5, right? Or whatever it is, whatever my y-intercept ends up being. This is just putting it into words. So I want you to know that it's not always possible to interpret my y-intercept. I'm going to write that here. And I'm going to just tell you, instead of writing it down, why or when it's not possible. It's not always possible to interpret the y-intercept for 2 reasons. So the first reason is when we have, and I'm going to show you a visual to go along with this, because I think that helps. When we have a data value that is close to the y-intercept, and I'm going to zoom this in so we can see here and possibly straighten it out a little bit. Look right here. We have this data value right there, right? It's really close to my y-axis, right? It's really close to x being 0 and whatever my y value is. In this case, I would not interpret my y-intercept, which would be way down here, because I have an actual data value that is close to x equals 0. So if you have a value of x that is close to 0 or a dot on your plot that is close to the y-intercept, you would say, I'm not going to interpret the y-intercept because I have a data value already close to that y-intercept. So you're not going to interpret the line there. So that's one reason. The other reason is nothing to do with the graphic at all. It's actually to do with the data and the context of the problem. So if you're talking about a problem like the height and the weight problem, if you said height is your x, right? A height of 0 inches makes no sense, right? So in that case, you would say that you cannot interpret the y-intercept because x being 0 or height being 0 inches does not make sense for my data, okay? So those 2 cases. So if you have a data value that's actually close to the y-intercept, or not the y-intercept, but the y-axis, or x equals 0, then you would not interpret. Or if x equals 0 does not make sense for your data, you would not interpret that y-intercept. Okay? And you would just write it out why you're not interpreting it. Okay. Let me zoom this back out. Sorry, I hope I'm not making you guys like motion sickness from that. Zooming in and out.
Could I see that y-intercept sentence again?
Sure. Yeah. Okay. So there's that. All right. So that's our slope and our y-intercept interpretation. Now, when you're using your technology or you're using your calculator, and you've already done this, if you started assignment 6 last class, you will get an equation of the line. You'll get A, you will get B. You got R, which that's why you did it to begin with the other day. You were getting R. Then you're going to get something else that's called R squared. Okay? R squared is the coefficient of determination. That's the next thing we're going to talk about. And this is why I don't like to call r a coefficient, because r squared is called a coefficient. Coefficient of determination. We're going to see some different notation, but we have r squared or r squared. So capital R squared or lowercase r squared. In general, the coefficient of determination is capital R squared. But since we're calculating the coefficient of determination based on the least squares regression line, we're actually looking at lowercase r squared. The notation doesn't really make a difference, but what I want you to understand is this coefficient of determination is actually our lowercase r that we calculated last class being squared. Okay, so lowercase r squared, this is the coefficient of determination. And this measures the fit of the line. And in our case, since we're studying the least squares regression line, it measures the fit of the least squares regression line. Okay. So r squared, capital or lowercase, in our case means the same thing, because we are actually studying least squares regression line, and that is our determination coefficient is our lowercase r squared. Okay. All right, let's talk a little bit about this r squared and what it shows us. So r squared represents the proportion. When I say that, I'm talking about the percentage of variation in our response variable that is being explained by the line. So r squared is the percentage of variation in the y variable that's being explained by the line. Now, since r squared is actually our lowercase r being squared, so let's think about lowercase r for us, our correlation value, that was between -1 and +1, right? So here we're going to see where r squared is actually between 0 and +1, which should make sense because when I square any number between -1 and +1, I will get a value between 0 and 1, okay? So just to give you like a little scale of what's going on, if 0 is over here on the left and 1 is on the right, as we get closer to 0, and I hope this makes sense to us, we have a poor fit of our line. And over here to the right, we have a good fit. Now, this should make sense, right? Because if our R, going back to last class, our correlation value, R, right? What did that tell us? R was telling us that linear strength, right? The strength of that linear relationship between X and Y. And if that was 0, it means there was no linear strength, right? So there was no relationship linearly between X and Y. So if I squared that value, it would be close to 0, which would mean I would have a poor fit if I tried to fit a line to it. I hope that makes sense, okay? So if I have a 0, that just means 0% is explained. So 0% of that variation in my Y is explained. And if I had a 1, what that means is 100%. So you're going to get a value between 0 and 1. You're going to change it to a percent. So 100% of the variation in my y variable is explained. Here. So let's take a look at an example, and we're going to write out this interpretation. I'll give you more of a template sentence, but it's this right here is my interpretation of my r squared. So let's take a look at an example of this. So for today's example, I actually took my pre-calc class. I'm going to try to leave that on there too a little bit here. And I looked at the number of classes that some students missed and their exam number 2 score. So leading up to exam 2, I counted how many classes that a particular student missed and their score on exam 2. And I just took a sample of 5 just to be easy, pre-calc students. And if any of you have taken pre-calc here at RIT, you know it's a very fast-paced course and you can't miss a class. There's just no way. You have to, there's too much material covered. And that's why sometimes I kind of pick on them and do examples based off them. So these are my individuals that I studied. Try to line them up. Now, just so you realize that individual 1 here missed 6 classes and earned a 73 on exam 2. Individual 2 missed 5 classes and earned a 75. So these are paired, right? It's paired data, X and Y. So the first thing we need to do before we do anything and calculate anything, I need to know which one of these is going to be X, my explanatory variable or my predictor variable, and which one's Y, the response variable. So we want to make sure we pick that out first. So do you think that the number of missed classes can predict someone's exam 2 score? Or do you think someone's exam 2 score can predict the missed classes? So I think it should be the first way, that the number of classes missed can predict someone's exam 2 score. So I'm going to choose this to be my X and my exam 2 score to be my Y. Okay. So that's how you figure it out. You just think about which one predicts the other one or could predict the other one. Sometimes it's a little tricky, and in that case, I tell you. Sometimes I tell you anyways, but in that case, I tell you because it's just something we don't need to be tricked up on. Okay. Now, if we're going to use our technology, we would take the numbers of classes missed and put that into list 1 in our calculator or column 1 in Minitab or whatever column you choose. And our exam 2 scores would go into another column, a separate column in Minitab, or a separate list in the calculator. It doesn't matter which way you choose it. Like this could be list 1 and this could be list 2, but all you need to do is label them. So then when you go back into your calculator or into Minitab and you tell either one of them which one's X, which one's Y, you know. Okay, you don't want it to be a guessing game. You don't want to put them in backwards. Okay, so that's my advice is just maybe write it down. Oh, I put this in list 1, this one in list 2, and then you don't have to go back and double check because you may forget by the time you enter your data and you go in to do your calculation. So we plug this into our technology, which that information was on assignment 6. So you can find that, the directions for Minitab or your calculator there. And when I do that, I'm choosing in my calculator y equals ax plus b, which really means y hat equals ax plus b because it's my predicted, it's not an actual. And here I'm going to find, now I've already done it, so I'm going to find that a is equal to negative 4.1154. And B is equal to positive 96.3462. And then I get R, which is negative 0.9914. And R squared is equal to 0.9829. Now you should have already done this on your assignment 6, and you get all this information. All we did on assignment 6 is we used R. Now today, and for assignment 7, we're going to use all of the pieces, okay, that's given to us. So here, now I can write my equation of my line, which is y hat equals negative 4.1154 times x plus 96.3462. Excuse me. And so there's my equation of my line. So now if I don't have to actually get a graph, if I wanted to predict values, I could. So maybe if I look up here at my example, I don't have anyone that missed 4 classes, so I could plug that in for X and find out what I would predict their exam 2 score to come out as. Okay. What's really nice, you can see here, this is a small sample. I can see there looks like there's a correlation, right? Before I even get my values, I could just kind of picture what's going on. I could see as X is increasing, right? As X goes from 0 up to 6, my Y is actually decreasing. So that just tells me my R value is going to be negative right from that. It tells me that the slope of my line is going to be like this in a negative way. I can picture it. Now, if you have a big sample, you can't picture it as easily. You can sometimes when the data is organized, but other times you just can't. But this is what's nice. You could just draw a scatter plot real quick with your technology, and you can see what's going on. You can see if there's a correlation. You can visualize everything because it's right there in front of you in a graph. So it's really nice to do that. So a lot of times we'll say, let's pull this up on a graph and just see what's going on before we do any calculations. Okay. All right, so let's talk about R and R squared here. So like we mentioned, R squared is this 0.9829. So let's interpret this value. So if we're going to interpret R squared, we're going to change this into a percentage. So I'm just going to move the decimal place over to the right 2, and I'm going to say 98.29. That's a lot. 98%. That's close to 100%, right? 98.29% of the variation or variability in my Y. So this here, my Y is my exam 2 scores, okay? My exam number 2 scores is explained or is being explained by, now I can write it out, the least squares regression line, or I can actually write out the equation of the line, and I'm just going to put it in parentheses here. So you can do either one. You don't really have to do both. But I'm going to do both. So I'm saying that 98% of the variability in these exam scores, right? The variability, right? The change in these exam scores from 73 down to, or up to 98 is explained by this equation. So you could just say by the least squares regression line. Sometimes I'll say specifically, give me the equation. You would plug that in right there. But that's the interpretation. Now, like I mentioned before, you don't have to use my exact template sentence, but you can. So the template is here where you would say the percentage here. You would say your Y here, and then you would plug in your equation of your line here. Okay, so that's the template. Right here's my R squared, my Y variable, and my equation of my line. Now, when we're doing interpretations, I don't want you guys to just say X and Y in your interpretations. I want to be able to read an interpretation and not guess what problem you're working on or what you're studying. I want to know that you're studying exam 2 scores, okay? And not just Y right there. So anytime we do an interpretation, we always put it in the context of the problem. So whoever's reading your interpretation, it's clear. They don't have to go back and look to see what you're studying. All right.